All right, let's jump right into this. Welcome to another explainer, where we are taking a really fascinating journey deep inside the human nervous system. Today, we're going to bridge a major gap. I'm talking about the gap between electrophysiology, those wavy lines we're so used to seeing on monitors, and the underlying cellular pathology, the actual physical truth of what's happening at the microscopic level inside our nerves. If you've ever wondered how doctors figure out complex nerve disorders, or why sometimes those standard diagnostic shortcuts just completely fail us, well, you're in exactly the right place. We are going to decode the signals, look directly at the tissue, and uncover the truth hiding right there inside our biology. So here's our roadmap for today's explainer. We're going to start by rethinking some common clinical cliches. Then, we'll cover the basics of saltatory conduction, acquired neuropathies, inherited uniform slowing, and finally, we'll wrap up with the rule breakers. Okay, Section 1, Rethinking Nerve Conduction Cliches. Let's dive in.
In everyday medical practice, neurologists use nerve conduction studies as their first line of defense. And over the years, three major clinical cliches, or rules of thumb, have kind of emerged. Number 1. If you see a conduction block or temporal dispersion on a screen, it just has to be an acquired demyelinating disorder. Number 2, hereditary neuropathies always present with uniform, even slowing of the conduction velocity. And number 3, axonal neuropathies basically just show up as a reduced signal amplitude. Now, don't get me wrong, these rules are incredibly useful on a busy clinic day. But relying solely on these wavy lines, it can sometimes lead us totally astray. We really need to look deeper.
Moving right along to Section 2. The basics of saltatory conduction.
To understand the pathology, we have to understand the normal physics first. Think of your nerve fibers like high-speed electrical cables. To keep the signal moving incredibly fast, they're wrapped in this insulating layer of fat called the myelin sheath. But this insulation actually has these tiny little gaps in it, known as the nodes of Ranvier. So what happens here? Well, it's pure biophysics. At each node, voltage-gated sodium channels pop open, and that creates an inward ionic action current. This generates a tiny electrical spark, an action potential, that literally jumps or leaps to the next node. This leaping process is what we call saltatory conduction, and it is the absolute key to our lightning-fast reflexes.
Okay, so this brings us to a really crucial concept, the safety factor. I want you to really wrap your head around this one. The safety factor is simply a mathematical ratio. It's the driving current pushing the signal forward compared to the minimum threshold current actually required to trigger that next node. In a healthy human nerve, this ratio sits really comfortably between 5 and 10. What that means is we have up to 10 times the electrical power we actually need just to keep the signal moving. But, and this is a big but, if a disease damages the nerve and this ratio drops below 1, the signal just stops entirely. Saltatory conduction completely fails.
And honestly, this brilliantly illustrates the physics of disease. When you put a healthy, perfectly insulated nerve right next to one with a damaged myelin sheath, it all clicks. When the myelin is stripped away or damaged, the nerve loses its tight seal. So remember that powerful driving current we just talked about? It literally leaks out into the surrounding tissue. It gets diluted. And because the current is leaking, it takes much longer for the next node to hit that electrical threshold. If the leakage is severe enough, boom, the safety factor drops below 1 and you get a complete conduction block.
That brings us to Section 3, Acquired Neuropathies and Myelin.
Let's look at a classic acquired disorder, CIDP, which stands for Chronic Inflammatory Demyelinating Polyneuropathy. In CIDP, the body's own immune system gets confused and attacks the myelin sheath, causing true segmental demyelination. The current leaks and the signal blocks. Simple enough, right? But because this is a chronic, ongoing disease, the body desperately tries to repair the damage over and over again. You get these concentrically layered formations in the tissue. Pathologists actually call them onion bulbs. They're literally formed by Schwann cells wrapping around the nerve again and again in these repetitive, kind of abortive attempts at remyelination. It's basically a microscopic scar of chronic electrical failure.
But here is where we get a massive, fascinating medical plot twist. For years, clinicians naturally grouped all these demyelinating-looking charts together. I mean, it looked the same. But recently, we discovered a completely different disease just hiding in plain sight: autoimmune paraneopathies. On an electrophysiology screen, paraneopathies present with the exact same slow conduction, the exact same blocks, and the exact same scattered wavy lines as classic CIDP, but biologically, a totally different ballgame. What is so structurally fascinating here is exactly how they're different. In paraneopathies, the immune system isn't actually destroying the myelin sheath itself.
No, instead, specific antibodies go after the molecular glue that attaches the end of the myelin loops directly to the axon. Those terminal myelin loops literally detach. They just pull away. And that widens the gap at the node of Ranvier, exposing these hidden potassium channels, which essentially shorts out the electrical signal. The current fails, creating a conduction block, but without actually destroying the myelin. It's a structural detachment, not a true demyelination. It just goes to show you that the wavy lines on a monitor can absolutely trick us.
Let's switch gears a bit. Section 4, Inherited Neuropathies and Uniform Slowing.
Inherited demyelinating neuropathies are basically conditions where the myelin just doesn't form correctly right from birth, and we can map these out visually to make sense of them. Essentially, genetic neuropathies fall into two distinct camps, those that cause a very predictable uniform slowing across all of your nerves, and those that just completely break the rules, causing random, non-uniform slowing.
Let's take the classic example of uniform slowing, Charcot-Marie-Tooth disease type 1A, or CMT1A. When you graph out the conduction velocities for this disease, it creates an almost perfect line. The velocities are uniformly slow in every single nerve segment. Why? Well, CMT1A is caused by the duplication of a specific gene called PMP22. Having too much of this protein creates a developmental defect. So instead of the immune system actively coming in and destroying the myelin, the nerve's insulated segments, the internodes, simply grow too short during development. And because literally every single internode in the entire body is uniformly too short, the nerve conducts electricity in a uniformly slow, incredibly predictable manner.
And finally, Section 5, the rule breakers, non-uniform slowing.
You know, biology loves to throw us a curveball. Meet HNPP, or hereditary neuropathy with liability to pressure palsies. Remember how CMT1A was caused by a duplication of the PMP22 gene? Well, HNPP is caused by a deletion of that exact same gene. This missing genetic information creates these bizarre structural quirks in the myelin called tomacula, which, fun fact, is actually Latin for sausage. And rather than uniform slowing, this genetic disease creates entirely random focal conduction blocks. It completely breaks that clinical cliché we talked about earlier. When you look at the actual cellular structure, the tomacula are impossible to miss. You get these thick, redundant loops and intense myelin infoldings. The myelin here isn't missing at all. It's practically overflowing and folding in on itself in these massive, sausage-like swellings. But these microscopic bulk-ups create severe mechanical vulnerability. Think about it. When a patient with HMPP simply leans on their elbow or crosses their legs, the physical compression against these tomacula squeezes the axon, creating sudden, localized pressure palsies. It's an inherited genetic disease, sure, but because we cross our legs or lean on our elbows at totally random entrapment sites, the monitor shows completely non-uniform, unpredictable conduction blocks.
And that pretty much brings us full circle. The shortcuts of electrophysiology. Assuming all blocks are acquired, or all genetic diseases are uniform, they're just that, shortcuts. The wavy lines on a monitor can absolutely tell us there's a leak in the cable, but they cannot tell us if the insulation was destroyed by rogue antibodies, or structurally detached to the loops, or if it was inherently deformed from birth by missing genetics. Electrophysiology absolutely must be married to cellular pathology. So I want to leave you with this to ponder. If our high-tech monitors only ever tell us half the story, what other incredible mysteries are still hiding in the microscopic architecture of our nerves, just waiting for the exact right lens to be viewed through? Thanks so much for joining me on this explainer, and remember, always keep questioning the data.